Hello everybody. I decided to try and make a video explaining orbits in terms of Newton and gravity and see if we can make some sense of the math behind this. The basic idea of Newton trying to explain gravity was what in the heck was pulling on the planets. If they were indeed going around the sun, something had to put them there, something had to keep them there. And in terms of the keeping them there, as long as they are in some sort of rotational motion, he needed a force to be pulling on the planets towards the sun. And in an effort to explain gravity, many of the parts of his famous work, Principia Mathematica, became the standard by which we do a lot of modern mechanics when we do physics. There was a lot of missing physics from Newton, but we still use a lot of Newton's work, even in astronomical work and even in space exploration. Many things had to have been changed and added. There are places where relativity has to show up, for example, and places where we have to consider the sort of flexibility of space time. But when you're thinking about the Earth going around the sun, using this idea that Newton put out there works just fine. So I'm going to start by playing this simulator from Nebraska Lincoln's astronomy department. And anybody who knows me knows I love to demonstrate these things. You can see the orbit of Mercury and Venus and Earth and Mars. And the orbits, like Kepler said, are not exactly circles. They're ellipses, even though for Venus and for Earth, for example, the eccentricity, which is the ratio of c over a, the center distance to the divided by the semi-major axis, that ratio, or the eccentricity, is very close to zero for Venus and for Earth, meaning that they have nearly circular orbits. Okay, I'm going to pause that, and we're going to switch a couple of things off, turn off all the other orbits, and we're going to pretend we're going to Earth. But then we're going to simplify things. We're going to make the eccentricity zero, and I'm going to play it again. The problem with doing orbits in a regular astronomy course is everyone is at different levels in terms of their math ability and their physics knowledge. So I acknowledge right now that if you have never heard about centripetal force, which is the force on an object being forced to move in a circle, being made to move in a circle, then a lot of this stuff is going to seem, bizarre to you. So there's to be confused is to be in the right place, and having to work through it as you learn how the mathematics works is meant, that's going to be part of the process. Those who have more experience, especially in a situation where you're sitting at a table with a couple of people who've had physics and a couple of people who haven't, this is where when groups are working on problems together, they really need to help each other out. All right, so I'm going to turn on a couple of physics features here. We talked about Newton's second law in physics. In astronomy. We actually haven't talked about it in physics yet. And I'm turning on a couple of features in the demonstration. The pink, or the center pointing one, is the force due to gravity, which I'm going to prove that to you in a couple of minutes, or at least we're going to use that assumption. And what it's being labeled as here is the acceleration. So another way of saying that is a centripetal acceleration. So something has to be forcing the object to move in a circle, because according to the inertia idea that Newton put out there, and lots of other people did too, but Newton labeled it as one of his three laws of motion. Inertia says that an object that has mass wants to fly in a straight line unless something acts on it, or it wants to stay stationary unless something acts on it. So something moving in a circle, like an orbit, immediately we're at odds with inertia. So I also would point out that the reason that orbits become stable over the evolution of a solar system is this rotational motion piece. So the fact that the gas cloud that was spinning already when the planets coalesced due to the gravitational instabilities within the cloud, that rotational piece actually lends itself to a weird kind of stability. Otherwise, as clumps would form in this gas cloud, they would be accelerated towards the center of the solar system where the star was forming, and they'd disappear. So the rotational piece, even though inertia says that objects want to move in a straight line, having things rotate actually adds an element of stability, which is a strange sort of consequence. So it shows how complicated trying to explain a mechanical system can be, when you add rotational piece, it actually makes it slightly more stable. The Earth is in a stable orbit. At least it has been for the last 4.5 billion years. And it has to do with this purple thing right here, the velocity. The fact that there is a velocity in a straight line. And I demonstrated this in class by spinning an angry bird on a string and letting it go. And you can see that an object experiences a center pointing force to move in a circle. But as soon as you stop that center pointing force, the centripetal force, it keeps going the way it was going, which is that tangential purple vector here, or velocity. So let's switch gears and try and do a little math. All right, so over here you can see that I've got a sort of a snapshot of that. You can see the Earth as the little gray dot, the sun in the center there. And I said in class that anytime an object is forced to move in a circle, the centripetal force is always the mass of the object that's going in a circle, in this case the Earth, times the velocity of the object moving in a circle, its tangential velocity, squared, divided by the distance from the center pointing force, or the distance from the center. So this is the mv squared over r equation, is the centripetal force. And this holds for any object moving in a circle, not just the Earth going around the sun, but any object. So you'll notice that m sub e is the mass of the Earth, and v sub e is the velocity of the Earth, which is that purple vector there, and r would be the distance between the center of the Earth and the center of the sun. And we typically just consider that 1 AU, and we don't get any more specific than that. I don't have to worry about the size of the Earth and the size of the sun, because it makes it easier. Newton also came up with what he called his universal law of gravitation. That's what I'm calling F sub g right here. And there was a giant variable there, which turns out to have a tiny little value. Not a variable, it's a constant. The universal gravitational constant that Newton actually did not figure out. That was someone later. But you have to multiply. What he did say is that the product of the two things, hang on, I messed that up there. The product of the two things pulling on each other, their mass, so the mass of the Earth times the mass of the sun, the product of their mass, divided by the distance between them squared. And this is one of the inverse square laws that shows up in astronomy all the time. So Newton just pointed out that there must be a relationship between the masses of the two objects and the distance between them, and that in order to get this to line up with what Kepler had seen looking at Tycho's data, Newton realized that there must be a constant in there to balance out the ratios that he saw in Tycho's data that Kepler had turned into his laws of motion. Newton recognized there must be a constant, but he never could quite nail it down. And one of the reasons is it's ridiculously small. Its derivation and discovery is its own cool story. So what I'm telling you here is that if we combine these two ideas, centripetal force and gravitational force, the thing that is actually causing the Earth to be pulled towards the center of the solar system, that is gravity. But if we want to describe that motion, then we have to use centripetal force. So if we put those two ideas together, centripetal force equation here, mass of the Earth, velocity of the Earth squared, divided by the distance to the center, if you set that equal to the gravitational force, mass of the Earth, mass of the sun, divided by the distance between them squared, it turns out some relationships between the various parts of an orbit stand out. First of all, I wanted you to see that the mass of the Earth actually falls out of this algebraically, that we don't actually need, in a system where the object that's going around is really small and it's in a circle, the mass of the object that's doing the orbiting is actually not part of the relationship. You'll also notice that one of the distances to the center, the r's, cancel out. And if we algebra this a little bit, yes, that's a verb I made up or use, then the speed of Earth squared times the distance of Earth from the center of the sun, that product, well, that was crazy, that equals the constant from gravity, that giant G that we talked about before, times the mass of the sun. And you'll notice that the stuff on this side, this stuff's constant. So if you want to figure out for anything going around the sun, if you need to know where it's going to be, all you need to do is get it up to a particular tangential speed, and that's where it will have a stable orbit. Or if you know where it's going to be around the sun, then you know how fast it is that it's going around the sun. So this idea, this VE squared R equals G times ms. The stuff on the right, this stuff over here will be true for any particular star. So if you replace, or an object going around the Earth, you could replace this as mass of big thing. So that could be the sun, that could be the Earth. It even could be something going around the moon. Whereas the stuff on the right, this is what I call the orbital equation. And what I mean by that is, all you need to know is the position around the orbiting thing or the speed. Those are the only two things you need. And or only one of the you actually only need one of those. So considering that for the sun its mass is not going to change when we're doing these calculations, and g is literally a universal constant, the stuff on the right's always a constant. So that means you really only need one thing. You either need the radius, which is how far you are from the sun, or you need the speed to get whichever one you don't know. So this orbital equation thing is extremely useful when we are attempting to do orbital mechanics problems. And typically all you'll need to think about is that product.